We're now going to turn to the study of infinite series. An infinite series is just a sum of terms which extends to infinity. These are useful when they converge to a finite number, as they allow us to represent all sorts of different types of functions. All the functions we've seen up till now are so-called elementary functions, but actually in reality most functions have to be defined in much more complicated ways than we've seen so far. One of these ways is through the use of infinite series. These come in the form of power series or Fourier series, as well as other types of series that you'll see later on. So to begin with, let's define a series in the following way. Let's take a sequence of numbers, which is infinitely long, and add them all up. So a sequence we define as a set. So it's a set of numbers A0, A1, A2, and so on. And we'll write this in a notation for the whole sequence as the set AN from n equals 0 to infinity, and then we just add them all up. And we add them up using a summation notation that we've seen before a bit for Riemann sums. So we add up partial sum, what's called the kth partial sum, where we sum up to the number k, and then we take the limit as k tends to infinity, and this gives us a way to define an infinite series. So an infinite series then is just a sum of infinitely many terms. The coefficients, the ANs, will typically be given in terms of a function. We'll see some examples just shortly. Let's see if we can figure out the ANs that go with the repeating decimal 0.11111. If we keep going forever for infinity, then we can write this as an infinite series. How do we do that? Well, let's write this in the following way. So it's the sum of these fractions, 1 over 10 plus 1 over 100 plus 1 over 1000 and so on. If we add those up infinitely many terms, we end up with the number, the decimal 0.1111. Now, why have I done that? Well, because I can use this to spot a rule. And so using this rule, I can figure out that the nth term is 1 over 10 to the power n. And so therefore, this is equal to the infinite sum from 1 to infinity of 1 over 10 to the n. The an that goes with this series is 1 over 10 to the power n. And note that we've started the series at 1 rather than 0. In general, you can start at any integer, including negative numbers. In fact, the summation notation is such that you can peel off some of the terms of the series. So for example, we could write this as 1 over 10 plus the rest of the terms if we start at n equals 2 to infinity. Let's have a look at an important example of a series known as the geometric series. So this is the series where we let the nth term be given by some number a times r to the n. So the previous example was an example of a geometric series. So a and r are real numbers. In the previous example, a was equal to 1 and r was equal to 1/10. But what about generally? Can I say anything about this series? If I add up infinitely many terms, what will it add up to? This is a question of convergence of a series. Note that in this case, each term is the last term times the number r, which is called a geometric progression. In fact, we can compute what this series adds up to exactly. And there's a trick that you can use to do this. So we let Sn equal the sum of terms up to arn minus 1, and we multiply by r. If I multiply this number by r, and now the trick is to subtract these two series. If I subtract these two series, what will happen is the ar term will cancel with the ar term, ar squared will cancel, ar cubed will cancel, and we'll just be left with the first and last terms in both cases. And this implies this Sn, which is the sum up to n minus 1, is a r1 minus r to the n over 1 minus r. Now, what does this tell us about the actual infinite series? Well, now I can let the number n tend to infinity. Now, if I take this limit, provided r is smaller than 1, this limit will converge to a finite number. And if r is bigger than 1, it will diverge. So if r is smaller than 1, modulus of r is smaller than 1, this converges. And in fact, it converges even if r was a complex number. We have an example of an infinite series which converges to a number, and that number we can find by direct calculation. We've also seen that some series converge and others diverge. Now, there's an important thing that follows from this. If I now let r equal x and a equal 1, I can get the following series. If a equals 1, I have the following important result. I can write the function 1 over 1 minus x as an infinite series, an infinitely long polynomial. 1 plus x squared plus x cubed, so an infinite polynomial, or what is sometimes called a power series. Let's have a look at just some other examples of series. We won't derive them. There's one called the harmonic series, And this is a series which actually diverges, but it diverges very slowly. It's a little bit like the logarithm function. There's also the alternating harmonic series, and this series is the same thing, but instead of every term having a positive number, I alternate the sign, and I can write this in summation notation, where we have a 1 over n that we had before, but to get the alternating sign of each term, I write this as minus 1 to the power n minus 1, so that as n increases, as n steps through 1, 2, 3, 4, 5, and so on, that just flips the sign of each term. And in order to get that right, I look at the first term and say, well, when n equals 1, I want it to be plus 1. So therefore, I want that to be an even number when n is equal to 1, and I can do that with n minus 1 or n plus 1 in the power. And in fact, this series converges, and it can be shown that this converges to the logarithm of 2. So that's an example of an irrational number with an infinite series expansion. In fact, many other irrational numbers have an infinite series expansion. A good example is pi. There's loads of different ones for pi. An example is this one. So 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths plus so on. That converges to the number pi, and I can write that as the sum of 4 times minus 1 to the n plus 1 to get their alternating sign, divided by 2n minus 1. And in fact, this converges extremely slowly. It's a nice example of a series which is really difficult to see what it converges to if you tried it on a computer, because you need around 500,000 terms in order to get the first 5 or 6 digits of pi. So in general, there's lots of types of infinite series. Let's just have a look at a few types. One is a power series, where I can write general sum, essentially an infinitely large polynomial. These are going to come up a lot in what we do. Others are a Laurent series, which is the same sort of idea. Now we let n go from minus infinity to infinity of the same type of thing. So instead of just positive powers of x, we have negative powers of x as well. There's something called a Dirichlet series, which comes up a lot in complex analysis. So if a number s is some complex number and I take the sum of some specified numbers a n over n to the s, this is called the Dirichlet series. And an important example of that is the Riemann zeta function, which is a function zeta of s of just 1 over n to the power s. So for every s in the complex plane, this evaluates to some complex number, or it diverges. And in fact, you can read up on the properties of this very special function. A final example is a Fourier series, which is actually quite a different type of series because it involves, instead of summing over powers of x, it sums over different frequencies associated with x. So it's a sum over cosines and sines where the number n regulates the frequency. And we'll see how we can use this, as well as power series, to represent all sorts of different types of functions.